Okay, here we go. That didn't take too long, right? So I titled this In the Packet Trenches. So these are all real world examples, things that I've had to troubleshoot, and it's broken up into two parts. The first one is I have two short examples just to get the juices going. Very easy, but it was more about teaching you the philosophy of troubleshooting, the steps that I take, and these came via email. So these are people who said, "Hey, Hansang, if you got a few minutes, can you just give me a hand here?" And and unfortunately, a lot of these problems can go on and on and on because people are not proficient at troubleshooting. So within, I think both of the first two scenarios took maybe, I don't know, 2-3 minutes to find root cause, right? But that's because obviously I've had practice. So I titled this to "Searching is Not Learning," right? So Werner and I were having lunch last night or dinner yesterday, and this is something that I always tell our SCs at Riverbed, right? Just because you search for something doesn't mean you learn something. So searching allows you to do something because someone said do X, Y, Z, but you don't really know why you're doing the X, Y, Z. Okay, so your job, if you're serious about doing packet capture or protocol analysis, you have to understand the protocol. There's no way around it. I say this all the time, but it's the truth. Okay, so my name is Hansang, in case you're wondering, and I've been doing this for a while, and so let's get started on our first European Sharkfest. If you have any questions, by all means, let me know. You just have to kind of speak up a little bit because there's a hum here. Only works if you practice. So again, wherever you stop, if you have some time, idle time, just open up a capture file, do your own packet capture, and just check it out. Hotels, airlines are great places because they offer you the most extreme in terms of latency, congestion, so those are good places to see. But keep in mind, right? So I always say this: if you've never seen a normal trace, you don't know what an abnormal one may or may not look like. Okay, so even when you're working, if you're allowed, if you have administrator rights, just do the packet capture. Okay, all of these slides will be available, so you don't have to. And that's the first one is just my YouTube channel in general. May or may not be all 100% packet analysis. Mostly it is. But the other one is the second one there is purely protocol analysis. The one thing I will do is I will put 10-15 minute videos of just a quick hit and run troubleshooting up there, and it'll go up there on a more regular cadence. Okay. So why do I talk about techniques and troubleshooting all the time? Because it turns out science is behind me. So if I were to, and there's obviously cultural bias here, if you step on the gas on this bus, which way would you go? Okay, that's the question. So think about that. If I step on the gas right now, which way would the bus go? Now, if you were wondering, well, I don't know, how it could be. Also, obviously, there's cultural bias here, but for the predominantly, you would say A. Okay. Now, if you're thinking, well, if you ask your children this, they will almost always instantly know that A is the front of the bus. Why? Because the door is not here. This is a school bus. I could have painted a red, bus in UK, but then you would go that way, I guess, right? So the idea here is that recognition starts with training, right? Everybody kind of get that, right? So this is why I always harp on the same technique over and over so that you don't forget, okay? Pilots go through a checklist for a reason. Military people, it's called PMCS. It's called, so you do this so that you don't forget. So that's what we do. We go through the same steps over and over, and we practice, okay? The other one. So again, there's some cultural bias here. I'm going to give you a quiz. I'm going to give you 30 seconds. I'm going to give you a task that you have 30 seconds to accomplish, and then I'm going to ask you a question. Okay? Simple as that. So the task is, in your head, do this in your head, obviously. Okay? You have 30 seconds to alphabetize the days of the week. Go. Alphabetize Okay, 10 seconds. Okay, think of a color, think of a tool. Color and a tool. How many of you thought about this one? So obviously people are laughing, hands go up. Why is that? Why did a lot of you, again, I know there's cultural bias, said, holy crap, how the hell did he know it was Red Hammer? Because your brain, when it's under duress, uses a short circuit technology. So it has a cache. Who knew, right? So your brain has a cache of information that when your brain is working hard and your CPU is at 100%, it uses this cache because it's busy. Why is it busy? Because the days of the week, something that we learned since I don't know, first grade, whatever, and it's very hard to put it out of context. Okay, for the same reason, when you count numbers out of order, so if next time you're having a nervous attack or you're nervous about something, try to count number out of order. Your brain detaches from whatever it's thinking about, worried about, and concentrate on the task of counting numbers out of order. Very unnatural act for the brain. For the same reason why I said Red Hammer, this is why we practice. Because you need to be able to pick up and spot things with a very short amount of time, okay? And because you're looking at all these traces and hundreds of thousands of packets, having this built-up cache of memory and tips and experience is how you can spot things that you may otherwise not. Okay, so anyway, first one, it's a slow start. It was a question about a slow start from email, and it was an online example from Packet Life, I think it was, and the person said, "Hey, I see slow start here, and in the description of slow start, it said packet so and so went together." And then 4 of them came together, and then 6 or 8 came together. He goes, but in the trace, it's every other packet is being acknowledged. What the hell? What am I missing? Okay, does that make sense? So we understand what slow start is, right? Slow start has to do with, it's like shifting a gear on a car, right? When we get on the freeway, we'd love to go 0 to 60 or 100 kilometers an hour in a few seconds, but most of us don't have a Tesla. Most of us don't have a Ferrari, so we go through first, second, third, fourth, fifth, sixth gear, and then we're up to TCP does the same thing, has to do with congestion window, slow start threshold. These are things, by the way, you should read about and learn because they're very, very important to throughput. Okay, so if you don't know what congestion window and slow start threshold is, that means you haven't studied and you need to look that up, and not just search. Not just search, but, okay, that was weird. Okay, so let's get started with our first example. Okay, we'll just power through, pretend that didn't happen. And this was what the question looked like. This is the actual email. The names have been changed to protect innocent. What am I doing? Okay, sorry. No. Okay, and this was the question, right? So in here, can you guys see that? So you can see here that there's Stephen's graph that shows the progressive clumps of packets coming. And his question was, you can see here, the commented, the original, the guy from Packet Life said, 6 and 8 were sent at the same time, and then 10, 12, 14, 16 are sent at the same time. But you can see here that they're all consecutive. Okay, the acknowledgments are all consecutive. So the packet wasn't describing exactly what this said. So where are these clumps of packets coming together that clearly shows slow start? And this is what the packet trace looks like. We can see here, I'm going to go to a simpler simpler profile, you can see here that the guy that asked the question is right. Okay, so if we look at, can you see the screen okay in the back of the screen, by the way? Yeah, is it big enough? Yeah, this should be all right. So you can see here, as I go down, the 192 and 168 guy is acting every other packet more or less, right? So that was the question. In the post, it said that these packets are coming together, but clearly it's not. Okay, and if you look at the Stevens graph, we can open up Stevens graph here under. You can see this is slow start, right? This is what the person was talking about. Couple packets here, more packets here, more packets here, more packets here, more packets here. This is first, second, third, fourth, fifth, sixth gear. And TCP goes off, takes off until there's congestion, okay, until there's packet loss, and then it recovers from that. So although the post was showing and talking about this, when we look at the packet trace, it's not, because it's every other packet is being acknowledged. So what's the deal? This is because there was no situational awareness for the person looking at this trace that asked me the question. You have to remember where you're doing the packet capture because it looks different. Okay, I'm doing this because in the big trace file that we're going to look at, the gnarly one, it matters what direction we're looking at. Packet loss looks different if you're on the transmitter or the receiver side. Okay, why would it look different? Packet loss is packet loss is packet loss. TCP is end-to-end. It's guaranteed. Why would it look different? So think about that, right? Again, I always say this, be that annoying or loving four-year-old that always asks why, daddy, why? Okay? Why would it look different from the transmitter side versus the receiver side where packet loss is concerned? Because if you're capturing from one side, the transmitter side, you've transmitted the packet. You saw that packet in the trace file. It got lost downstream somewhere. So the receiver will see a clear gap where the packet doesn't show up. But from the transmitter side, you can get confused because it'll say, what the hell? I see it right here. Where's the packet loss? Because it happened downstream. So the symptom looks different for a packet loss from the receiver side, where clearly there isn't a packet, and the sender, where the packet is in the trace file. Okay? So these are things that can trip you up when you first start out. So orient yourself. Okay, and there's some tools, tips on how to do that. The easiest one is if you have the SYN, SYNAC, and ACK. You need all three. And so I know this is kind of the basics, and we have 3 fins here in this advanced topic, but I'm kind of building up to it. This is where are we closer to? Are we closer to 192 guy? Are we closer to 174 guy? 192 here and 174 here. Okay? And I'll zoom in. So it should be clear that we are on the 192 side, right? Why? Because that packet number 1 there that you see is a moment in time. Okay? Nothing existed. That's the Big Bang moment. All of a sudden, we see a packet 192, 168 sending to 174. But at this point, we don't know where we are. Okay? But the SYN-ACK, which is packet number 2, happens 46 milliseconds later. Okay? And then the ACK is immediately seen. So when you diagram this out, okay, you'll know that you must be either at 192, 168 or very, very close to 192, 168. Okay? And by very close, I'm talking about maybe in the same data center, same physical location, because there's only microseconds of delay between hops. Okay? The other way to confirm this is sometimes it helps to look at the MAC addresses. Doesn't always help, but sometimes it helps. Okay? Because if the destination is to a networking device, that means typically it's host to networking device. But if it's Juniper to Juniper, Cisco to Cisco, Cisco to Juniper MAC address, then you're not capturing at the client, you're very close to it. Okay, does that make sense? Another one to look at is time TTL. Okay, you can see here TTL 64, it hasn't gone through a router because the other alternative is that this TTL, time to live, is 128, and we went through 64 hops before we got this packet, which is very, very unlikely. Okay, so remember, time to live is how routers subtract a TTL, and we do this so that we don't have a loop. Okay, if ever there's a loop at the IP level, TTL will eventually kill the packets. All right, make sense? Okay, so the original question. So the original Stevens graph clearly shows clumps of packets. You saw that 2, 4, 6, 8, and the steep slope on the Stevens diagram. But on this trace, it doesn't look that way, does it? So here's the ACK. Here's the get dummy. You can see the client making the HTTP get. We see 48 milliseconds later, TCP saying, okay, I got you, I heard you. And this is length of 0. So this is just the beginning, the ACK saying, okay, I heard you. Then the packet comes, we acknowledge, packet comes, we acknowledge, packet comes, we acknowledge, packet comes, we acknowledge, packet comes, we acknowledge. This was the confusion. In the post, it said 4 and 6 left together. So here's 4, here's 6, but it doesn't look that way. Why? Because you have to have that situational awareness. What's the time round trip latency between these two sites? 40 some odd milliseconds, right? 46. That's about, for the States, New York to a little bit past Dallas, Texas. Okay? By the way, how do I know this? Because I'm assuming most of you are in networking side of the house. So in your network, you should know by heart what these normal latencies are. Okay? 72 milliseconds is London to New York. I know the guys from Bloomberg know that. I know that because if you're in the financials, those market, Singapore market, Frankfurt, Hong Kong, these are things that where latencies can kill you, so we know it by heart. So 46 milliseconds is how far these two things are apart. Okay? So although it looks like I see here an acknowledgement happening right away, an acknowledgement happening right here, okay, we have to realize that this packet, this one and this one left the train at the same time, and we're acknowledging here. And although it looks like we're acknowledging every other packet, look at the time from here to here. Okay, so packet number 6, 7, 8, 9 all happen in millisecond or less. Okay, which means although I'm acknowledging, the 174, this one and this one had to have left at the same time. Because otherwise, I would see a 48 millisecond delta between clumps of packets. That makes sense? Okay, so here's the next one, and here it says, okay, I'm acknowledging 2921, and so the next sequence number is 2921. So clearly, packet number 9 is acknowledging 8. Then, although I'm acknowledging here, you can see from the time it takes from here, so let's set this as the beginning of time. Okay, we know that this is we paid the round trip penalty. I hit Control T, and the next round trip time penalty happens down here somewhere. There it is, packet number 18. Which means from the sender's perspective, the 172 guy, all of these happen in near real time. This is why it looks very different from the client side. On the server side, you would see exactly what the post said. I sent 2 packets, I got an acknowledgement back 48 milliseconds later. I sent 4, I sit tight, I see an acknowledgement. It's cleaner if you had captured this packet from the other side. Okay? But this is important trace because, yes, slow start, we get it, we understand it, but it presents itself very differently from one side or the other. Okay? Does that make sense? Okay. So I'm building up to it. So if by the way, If you're sitting there wondering, what the hell is he talking about? I'm sure there are others in the room thinking exactly the same thing. So don't be shy about raising your hand and saying, wait, I don't get that. Explain that again. Give me a different analogy. Okay? Otherwise, you're going to stew about it. You're going to forget about it. And that's not what the spirit of Sharkfest is. I'm here to tell you, and I say this every year. I've been to every one. Very proud of that. Almost every one. I've never been late until today. But instructors all go to each other's classes and we all learn from one another. Okay? There's never a time where you're like, I'm here. I understood everything. There's nothing else for me to learn. That doesn't happen. Okay? For a couple of reasons. Yes, there's a question in the back. Yes, absolutely. So the question was, will I share these files? The answer is absolutely I will. When this PowerPoint goes up into the retrospective site of Sharkfest, it will have a download packet capture link, and it will all be in there. So why don't I do it beforehand? Because I know what happens if I give you a link saying this is the trace file. You're all going to go download it, and you're going to start digging into it and not paying attention. Okay? Because that's what we do, right? We want to troubleshoot, and so that's why it's not available ahead of time. Okay? Different philosophies, but I want you to pay attention and soak up what it is that I have to say. You paid good money, obviously, to be here, so sit back and then follow this recording and do it with the trace file in your on your PC. Okay? All right. So moving on. The second query comes from IPsec. And this one took all of 15 seconds after opening the good working trace file and non-working trace file for me to give root cause and move on. Okay. When I said this is an IPsec example, from a troubleshooter's perspective, IPsec means a couple things. One, the SAs, the security associations, are not coming up because there's a mismatch of ciphers, etc. You've offered this, and the other guy said, sorry, not going to do it. IPsec can also fail if there's an intermediary device that's stripping stuff from you. So there's a NATing device, a firewall device, or proxy, a terminating proxy that munges your request to form the SAs. Okay, that one's actually not too bad to troubleshoot because you never get past certain stage of IPsec, phase 1, phase 2. Okay. Again, if you're a network engineer, we've all used router-based encryption. You should read up on IPsec and how it works. The difference between searching and learning. Okay? So if you know the protocol IPsec and how it works, then it's much, much easier to troubleshoot. So in this case, clearly it's not an IPsec problem itself because the SAs are just fine and the transfer is happening when it's working. It's only that this site doesn't work. So I've given enough clues. In one site it works, in one site it doesn't. What's the most likely cause of that in an IPsec world? I'm sorry, what was it? There's in the back? Out of order? Okay. So out of order means there was some kind of congestion along the way and the packet showed up out of order. In the world of TCP, it doesn't matter, but in the IPsec encapsulated ESP, it may or may not matter, but TCP that's inside will recover. Okay? Another. Okay, network address translation for IPsec is okay, so long as you're not using authenticated headers, right? So to the anti-spoof, but these are all things that we want to check off our list. Okay? By the way, just a quick corollary because it matters for the final trace that we're going to look at. Ever wonder why it's called a triple duplicate for a fast retransmission? Not 2, not 4. It's like a Monty Python bit. The count shall be 3. 3 being the count shall be the count. Anybody remember that? 4 is right out. Okay. Why? Because it was just in case a packet comes in out of order, you don't want to adversely react. When a packet comes out of order, you don't want it to say, oh, it must have been packet loss, fast retransmit. No, just sit tight. Because chances are it's okay. But if the duplicate acknowledgement happens 3 times, you can reasonably conclude there was packet loss. So there wasn't much science behind it. They just said to not act too quick, let's do 3, but let's not wait forever for like 4, 5, and 6. Okay? Does that make sense from a triple duplicate? I'm building up to it because that has a very much an impact on the final trace file that we're going to look at. And I'll explain it again if fast retransmission versus timeout doesn't mean anything. So here's the working one. And what do I do? If you guys know my workflow, I just scroll down just to get to see what's happening. And being that this is an IPsec problem, I'm looking at a particular column. I'm looking at the far right side to see if there are any alerts from an IPsec level. It's not, because I'm already into 400 something packets and the flow is happening just fine. I'm also noticing that I just saw that, but that's okay. That's DNS. Okay, I chopped off DNS. That's why it's malformed. But you see a lot of 1500 byte packet, right? MTU, full size packets, MSS of 1460. Okay, so the one thing that nobody shouted in IPsec world is fragmentation. So why do we have to worry about fragmentation? Because IPsec has an overhead. Okay? If you GRE and then encapsulate the GRE packet, for example, you have to make room for GRE, you have to make room for ESP, which means you don't have the full MSS anymore. The easiest way to do this is, if your carrier allows it, is to make your MTU on the WAN side 1600 bytes. If you're not using jumbo frames. Why 1600? Because that accounts for GRE, AH, and ESP. And you don't have to fragment the packets. And you might be looking at me saying, that's okay, Hansang. I'm using MSS TCP adjust, and I adjust the SYN/SYN-ACK. So let's go back to the very beginning. Not here. But in the SYN/SYN-ACK, it says, hey, the maximum segment size I can do is 1460, 1460. If the router along the path modifies that and says, I know I have IPsec GRE here, I'm going to crank it down to 1428, that's a kind of a cheat. We're asking the router to do something it wasn't really designed to do, right? It's more of a cheat than allowing path MTU discovery to work. Okay? So the better way to do it is make sure path MTU discovery works. Okay, so that end to end, they can determine what the smallest MTU is along the path. So clearly this is a working one. And let's look at the trace that's not working. Here's some couple of SYN/SYN-ACKs. And the MSS is in the TCP option. Here the guy says 1430. That's good. And we scroll down. And immediately, what do we see? So there's a lot of IP addresses in use here. But for the most part, do we see any 1500 or 1514 size packets? There was 1 or 2 there. But you can see how it's 1464, right? And if we click on that 1464, length is 1410. Okay, and it happens again and again and again. Okay, remember there's a bunch of conversations here. Some are working, some are not. So if it's IPsec and you see smaller size packets, you should immediately type the following display filter. Okay, besides checking for TCP analysis.flags, besides checking for delta, my usual workflow. Given that I was a little tardy, I'm short-circuiting my usual workflow, if you were wondering. And that display filter is ICMP type 4 and ICMP code, ICMP type 3 code 4. Oops. This is not working. I'm sorry. Although, why did that work though? It is type 3 and code 4. I must have mistyped it, right? Because it is type 3 and code 4. Anyway, ICMP type 3 code 4 says type 3 code 4 is I need to fragment this, but I can't because you told me do not fragment. Okay? Because in the IP header, there's a do not fragment bit. Why is there a do not fragment bit? Because if I said that, some router along the path is forced to send me an ICMP type 3 code 4 message saying, hey, here is your original conversation, 152 to 14. Along the way, MTU of next hop is not 1500, but it's 1492. This is the slowest MTU, the smallest pipe size from point A to point B. And some random router along the way sent this to me. Okay? So a couple of quick things. If you are only capturing from the original source destination of the IP address you see here, okay? Remember where we are. We are inside the ICMP message. So this is a copy of the original IP address. So if you're only capturing from this source to this destination or this conversation, you would have totally missed this ICMP message. And you would still be troubleshooting. Well, you wouldn't be, but. Okay? So whatever filter you use, whatever BPF, whatever filter you use, always put a parenthesis around it and do or ICMP. Okay? Because it's important. ICMP is a control message protocol. It's designed to tell you when ports are not available, when access list is blocking it, when the destination can't be reached, etc. It's very important to troubleshooting. So whatever filter you use, always parenthesize it and say or ICMP. So the question was if there's a different IP conversation or? Uh-huh. Oh, so what happens if there are more than so a bunch of different MTU sizes, right? Every router along the path, you would see it as consecutive MTU. So you fix it, and the next one says, sorry, it's too big, cut it down. Okay, so it's like traceroute. It happens one at a time. So as I see, because what happens in ICMP Type 3 Code 4 is this. The host machine builds a routing table dynamically and adds smallest MTU size that it sees. So if I overcame the first smaller MTU size and the next one down is smaller, the routing table in my host table gets updated saying, oh, you know what? It's now even smaller. Now it's 1400. So then the fourth router along the path says, sorry, MTU is only 1300. Then my routing table gets updated and says, okay, only 1300. Okay? So when you do path MTU discovery, you remember that because you update your local routing table. Okay? So if you do a netstat command, even in Windows, you'll see the biggest MTU size recorded there. Okay? This is how path MTU discovery works. And this is how the host knows to shut it down to the MTU size here. Is that okay? So again, the question was, if there are multiple MTUs along the way and smaller and smaller and smaller, what happens? You would see 3 or 4 of these ICMP Type 3 Code 4s coming back at you. And you keep adjusting as you go along. Okay? Make sense? Easy, right? So the answer is right here. Some random router along the path that you may not have control over just told you to make it smaller. Okay? So why doesn't this always work? The one thing that you have to be concerned about in the world of Cisco is this. If you have a choke point, so this is a VIP, for example, okay? Most of us use virtual IPs and load balancers, and it's hosted by a router here of some sort and going to multiple sites across. There's rate limiting built into the routers to protect itself from a DDoS attack. So ICMPs are rate limited. Okay? What that means is if you have an operation where some big honking box updates a bunch of point of sale systems at the end here, or it's a database download to a bunch of branches at the remote site, or you're updating, some file for, it could be antivirus, it could be whatever, and you're sending out a bunch of updates to a bunch of different clients simultaneously, and within a second, ICMP rate limiting kicks in. Okay, and you'll have mysterious failure where one branch is working one day and the other one doesn't work, or one day it works, another day it doesn't work. Okay, and what's happening in that case, more than likely, which was the case here in the example that I showed you, is that the router here has a choke point. The MTU here is smaller, so it needs to send ICMP back to the server sending the data, but it misses a few. Why? Because I updated this. So let's say in my example, the first 4 asked the question. Okay? And the server says, I'll give you that file. Bam, 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 bam. He sends out 4 independent TCP conversations to the remote site. The first 2 will make it just fine. The next 2 will not make it, because within that first second, my rate limiting factor was 2 ICMP messages per second, but not 4. Then the cycle repeats itself. After that 1 second has gone by, branch number 5 and 6 get the ICMP messages, so they reduce the MTU size, but 7 and 8 will not, because within that 1 second, 4 branches tried to get updated. Okay? So in the world of Cisco, just look this up. IP ICMP rate limit, unreachable, do not fragment, and how fast you want to reply. Okay? So this command, the DF, so there are multiple unreachables, right? Administratively prohibited, port not available. There are different types of codes, but that DF there that you see says, I don't want to do this for all of them. If the port's not unreachable, port's not unreachable. I don't have to worry about that. Okay? Whether the port's unreachable because I'm blocking it or someone else is blocking it, port's not available. So it's not as important as this one, which is do not fragment. So this is saying for the IP stack, there's an ICMP sub protocol. There's a rate limit command for unreachable, particularly do not fragment. Type 3, code 4, respond every 50 milliseconds. Okay? So even in cases where you have this, it's very unlikely, because a wide area network is involved, that you'll have an issue. Okay? You can crack that down to smaller for internal use. So anyway, you just need to be aware of this. Okay? Any questions so far? Okay. What was the time again? The 10:45 is the ending. Okay, good. So we'll take a break from 10:45 to 11. Is that right? Yes. Okay. All right. So I'm going to tee up the next packet trace file, explain it. We'll have a 15-minute break, and I want you to think about the problem that I just described to you in the packet trace, and then we're going to solve it together when we come back. Okay? So we're going to spend almost an hour and 15 minutes, hour and 15 minutes on one trace file, because it has all the different things that could go wrong went wrong with this trace file. Okay? All right. So let's go to training. Okay, so what is the deal with this? So these are a bunch of VMs on an ESX, sitting on an ESX, talking to a NAS, okay, network attached storage. And in the world of ESX, you can do it a bunch of different ways, storage attached, whatnot. In this case, this was NFS host. So there's a IP address, which in this case is 10.10.10.10 you see there, who's acting as an NFS host to the NAS. Okay? So when the client inside the ESX on the hypervisor says, hey, directory C, copy this file, in the real world, it's happening via NFS to the disk. Okay? So remember, you don't really have a disk. Well, you have a small subset of disk, but the real disk for your entire virtual machine is sitting off to some NAS somewhere. Okay, and that happens via NFS. So one word of caution I will tell you is that it's much better if you put those NAS, whether it's NetApp or some other vendor, it doesn't matter. Whatever your NAS solution is, try to put it on the same ASIC as that ESX port if possible, because there's actually there will be a line card impact if you go outside of ASIC to ASIC. So on the switch port, there's 2-to-1, 4-to-1, 8-to-1 switch port to ASIC mapping. Okay, so depending on what equipment you use and what line card and what model, follow up and get the documentation. And if you can, and you have the luxury, you can put it on the same ASIC, which means it never leaves that ASIC, which means it's the least impacting to other traffic along the. If you go from line card to a line card, then there's a backbone impact. Okay, and hypervisors and network attached storages have no qualms about saturating that 10 gig pipe. Okay, so if you have the luxury, and I think there's actually a microburst session later this afternoon, if I'm not mistaken, and you're going to see a bunch of that. A microburst where you go to line rate all the time, every time, causing you all kinds of grief that's hard to find. Okay, so those of you in financials, you know this, but that's why I'm saying try to put it on the same ASIC. Okay, any questions about that? All right, so in the trace that you're going to get, you're going to be missing a couple of things. There's NFS involved here, and it's not important. We're not troubleshooting NFS. But I left it in so you can see exactly what the question being asked and NFS request was and what the answer is. Okay? It's not strictly required, but it helps if you have context. The trace file that you're going to get will not have that because I'm going to use Jasper's Expert Trace Wrangler utility to cut it off at the TCP level. Okay? Because there are some host names in there. While not sensitive, you can't reach it. Still, I don't want to put it out there. Okay? So keep that in mind. Note to self as you're watching this video, the trace file that you have and looking at right now will not have those NFS read-write requests, but you'll be able to follow along. Okay? So keep that in mind. So what do I always do? I always page down because that's just my workflow, and I want to see what's happening. Full-size packets happening in clumps. I see here. I just saw NFS read-write request. Okay, if I scroll back down, there it is. Okay, even though I'm going very, very fast, I've seen this one, number one, but as I'm going scrolling down on the right-hand side, I'm looking for changes in pattern on this side. I'm looking for changes in pattern here. I'm looking for changes in pattern here. Sometimes I don't necessarily look at the change in pattern here because I will look at this separately. Okay? So in my mind, I'm looking at, are there anything that's happening here? Do brackets show up? Bracket is Wireshark telling me something. Okay, so if you see all of a sudden see a bunch of brackets, Wireshark is trying to tell me something. Even though I'm going down fast, you'll be able to spot that. Okay. What else is going on here? Full size. I get it. Oh, there was some back and forth there. I stopped here because this looks a little bit different, right? This looks different than what we saw earlier. Why is it different? Because all of a sudden I'm seeing 2 act, 2 act, 2 act in terms of this. Okay, so let me go up a little bit, show you what I mean. So you see the clumpiness of that 1500? You're not looking necessarily at exactly that number. You're just looking for the length and changing pattern. Okay, let me scroll back down. For the most part, we saw all of this happen, and then all of a sudden at some point here, we went to, you guys see that? Okay, so that's, you make a mental note, I should go take a look at that. Why did this change, this behavior change all of a sudden? If I saw a huge bulk transfer where I saw all these big clumps of full-size packets coming down, why then does it all of a sudden go to Q&A type mode where we see 2 and act, 2 and act, 2 and act, 2 and act? I'm not saying there's anything wrong with it. I'm just saying this is a person of interest. You should go take a look. Okay? This could be as simple as I'm done doing the bulk transfer. I'm now negotiating directories and files that I want and offsets, etc. So this could be part of the protocol. Maybe nothing wrong, but again, person of interest. Okay. So, okay, I'm dealing with big honking transfer. I know that because the delta time as I'm scrolling down is measured in microseconds. Okay, because the first part of this is all 0. And I'm seeing clumps of 0. And all happening here. So this is a big fat pipe, and it's transferring a lot of data. Okay? Everybody makes sense why I do this? Okay? I'm just getting a feel for it, that's all. So some of you say like, it's a waste of time. That's okay. Use whatever method that works for you. Remember that memory map, that red hammer that I talk about? This is my red hammer. By doing this, my brain is trying to keep up with a swarm of data, and already automatically starts using memory maps to try and make sense of it. And by training my brain, I can pick out little nuanced changes quickly. Happens with practice. Okay? It's like that old saying, how do you get to Carnegie Hall? Practice, practice, practice. Right? You've all heard that. So this is what we're doing. We're practicing, practicing, practicing. Okay, so I have a very good feel. I do this to about 5,000-6,000 packets. There was something that caught my eye there. What caught my eye? I saw a bracket there, so I kind of just stopped just to see. And there was something else there. We went from bulk transfer to, again, choppiness. Okay, so these are the types of things that I'm looking at. So that choppiness that I saw earlier is not a one-time event. I'm seeing it again and again and again. So now I'm trying to, it's being deprioritized because it seems to happen again and again and again. Okay, so it's not a one-time anomaly, so maybe it's part of it. Okay, big bulk transfer, big chunks of data being transferred, a little bit of back and forth there. And okay, so I'm at about 5,000. I know my lay of land. I saw some brackets fly by there, TCP segment reassembled. I saw this, read write. So this is the NFS read write, how much data it wants to see. Got it. My next step is to do TCP analysis.flags. This is the bone of contention for many. My workflow says, unless you're really, really worth it, I'd rather just type you in than click on it. And yeah, there are cases where I may temporarily use a button, but so far this is the only thing that was worthwhile for me to use. TCP analysis.flag. That's all it's doing. And I see here immediately the brackets that I saw earlier. Okay. DUPAC 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then fast retransmission. So right there, Wireshark is telling you this is a fast retransmission. Okay. So when you see a retransmission, Wireshark is telling you it saw the packet twice. Okay. From the sender's perspective, you may not see it. You may have all the packets accounted for, but at some point, that fast retransmission at the bottom of the screen there was retransmitted, but it was a fast retransmission. Fast retransmission occurs because you got 3 duplicate acknowledgments saying, I didn't get it, I didn't get it, I didn't get it. After the third time of hearing, I didn't get it, I didn't get it, I didn't get it, you're going to retransmit immediately. Okay? There's other things that happen from a congestion window and slow start threshold. Important to remember, but outside of the scope of this class, so look it up. Okay? Fast retransmission, you don't pay much penalty. So that's good. What else is happening? Same thing, right? There's a fast retransmission and a bunch of packets getting lost. Or is it? Remember, this is all for one packet loss event. But I saw 29 duplicate acknowledgments for the same thing. This is saying I lost this particular segment, source sequence number. Okay. Hey, I lost a chunk of data. I lost a chunk of data. I lost chunk of data, chunk of data, chunk of data. And I just told you 23, 24, 5 times that I lost the data, and the fast retransmission happens here. And you might be thinking to yourself, why the hell did you say 29 times you lost the data? Why is that? I thought triple duplicate meant 3 duplicate acts and you get a fast retransmission. That's what I just said. But in reality, it doesn't look like that. Why is that? So I want you to think about that. Okay? We're going to take a quick break. So think about that. I just said triple dupe, fast retransmit, and here I see 29 of them. Okay? All right. In the interest of time, the next thing I'm going to do is clear this thing. My next thing that I do in the workflow is delta time is displayed column. I click on delta. I scroll all the way to the bottom because this is my persons of interest. Okay? Immediately, something shows up in my brain. That red hammer just went off. I see retransmission taking 2-300 of milliseconds. That's a red flag. Fast retransmissions don't take this long. So what the hell? And then Wireshark is telling you that's not a fast retransmission. That's a TCP timeout retransmission. There are big penalties associated with regular retransmission. Okay? The other thing that happens, there's a preponderance of 100 millisecond delays with nothing but ACKs, naked ACK. There's no data going back. This is just the acknowledgement. Boy, we are paying a 100 millisecond penalty and boatloads of them. That will kill your throughput. If you have to stop for 100 milliseconds, that's an eternity, you're going to cause and pay a huge penalty. And remember, this is a VM transfer throughput issue. So I think I found the root cause here. Maybe, maybe not. We'll start peeling the onion when we come back in 13 minutes. Okay? So at the top of the hour, we'll pick this back up. So think about what I said, fast retransmission, timeouts, why did I see 29 duplicate acts, etc. And I'm going to pause the recording here. All right, so we're back from the break. And I had asked, I'll edit that out. I talked about the retransmissions, the fast and the non-fast kind, and all the delays that we see here when we sort it by the delta column. And notice that the biggest delay of them all are all retransmissions, and it doesn't. The Wireshark there doesn't say fast retransmission. Okay, so why is that important? It's important for a couple reasons. Number one, if you see the same segment, the same packet repeating itself, you're going to see doubling of time on the delta column, and that means it's a complete blockage. So that's a good hint. Okay, you see the same packet, same data, same segment trying to get retransmitted over and over, and the delta time doubles. That's the back-off algorithm that TCP uses. So that means it's a complete black hole. Okay, so that's important why you sort by delta and look for the same. So this one doesn't look to be the same. You can see here down here the sequence number changes. Okay, so it's not the same packet, obviously. But this is another clue that, okay, so it's not a complete blockage, okay, because it's not doubling in, the delta time is not doubling in time. So it's not an access list problem. It's not a black hole like a firewall or something. So we rule that out. But the retransmission that takes this long can happen because of a timeout. So why does it happen? So if I'm sending you packets, okay, and a packet gets lost, it forces duplicate acts to be generated from the other side, right? So I sent you 10 packets. Okay, let's go through this in our head. In your head, think about 10 packets, 10 trains leaving the station at the same time. All 10 trains left this station from the sender's perspective. Packet number 5, train number 5 goes missing, okay? So on the other side, when you're receiving the packet, you're going to say train number 1, 2, 3, 4, 5, all good. Oh, all of a sudden, I count to 4, and then I see train number 6. And I ask, where's train number 5? Train number 7 comes into the station. I say, I still haven't seen 5. Train number 8 comes into the station, and I say, I still haven't seen train number 5. Train number 9 comes in. I still haven't seen train number 5. Okay, that's 3 duplicates, and then I fast retransmit. Okay, yes, there was a question in the back. Was there a question in the back? No? No, okay. So that's what I'm talking about, triple duplicates, right? Everybody understand that? Okay. But what happens if train number 10 goes missing? So 10 stations left, or maybe train number 9 goes missing, or train number 8 goes missing. Okay? So in this example, let's go with train number 8 going missing. Okay? 1, 2, 3, 4, 5, 6 arrive. And I acknowledge every other one, etc. I get train number 7, 8 goes missing, 9 shows up. And I say, hey, I haven't seen 8, my first duplicate act. Train number 10 comes. I haven't seen train number 8, second duplicate. But that's the end of the train. So now we both wait. I don't have another packet coming to me to induce 3. I'm missing, which means fast retransmission cannot happen. So what happens? So every time a packet gets fired, the TCP stack has a bunch of different counters and timers. One of them is, have I gotten an acknowledgement yet? It can be 100 millisecond delay, 200 milliseconds delay, 400 millisecond delay, 500 millisecond delay. Okay? There's a timer that says, I can't wait forever, so I'm going to wait X amount of time, and then I'm going to just assume the packet was lost. So you end up wasting hundreds of milliseconds because there's no feedback coming. Okay? So we'll see in this example that that's exactly what's happening. The tail end of a packet train leaving the station, if the tail end goes missing, nobody knows. Okay? Make sense? That's why if you saw old Western movies and the old Army movies, they always say kill the people from the back of the line in the patrol because people in the front won't notice. That's exactly the same scenario, although it's a morbid example, but that's what happens. Okay? So that's what's happening here, and we'll see this in detail. The other thing that I had asked was, why did we see so many duplicate acknowledgements? Never mind triple duplicate. I see up to 25, 24, 25, 26 here. So at some point in this example, okay, that's my first of the triple duplicate, second and third. By this time, I'm doing a fast retransmission. Okay? And yet here I see 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? This is my packet train leaving the station at the same time. Because I have a pretty decent send buffer, because I have my receiver window size that's big enough, okay? My receive window size is fine. My send buffer is big enough. You can't see the send buffer, by the way. It's not exposed in the packet. So the sender says, I got plenty of bandwidth buffer. The receiver says, I got plenty of receiver buffer. Go ahead and send me as much as you can. And so in this case, 20, 30, 40, 50 packets leave the packet station at the same time. And of the 25, 30 packets train that left the station, if train number 4 goes missing or train number 5 goes missing, guess what? I got 20 other trains that are pulling into the station after that event. Okay? Imagine 25 trains leaving the station at the same time. After the first 4, the packet number 5, train number 5 goes missing, I still have 20 more trains coming in. Okay? That state already left the station on the other side. So that's why I'm generating all these duplicate acts. Okay? So in your mind, think about this. In your mind, 25 trains left the station at the other side. Train number 5 goes missing. I have 20 more trains that are going to pull into the station. Each one's going to generate, I'm missing 5, 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 I'm missing 5. Okay? So, let me ask you a question. Given that we see a pattern of 10 to 20 duplicate acts and 1 fast retransmission, and in this particular case, there's a TCP timeout retransmission. Am I using selective acknowledgement? Yes or no? Yes. Without even looking at the details, I know for a fact selective acknowledgement is in use. Because if selective acknowledgement was not in use, what would this look like? You would see a load of retransmissions. Okay, so let me explain that. So it wasn't that long ago that TCP has, the positive acknowledgement that we talk about. And basically it says TCP acknowledgement is cumulative. I'm good up to packet 5. Here I'm using the concept of packet, but it's really not packets, right? It's how much data I received. That's what sequence numbers are. How much data have I received? Totally immaterial of the packet itself. Okay, because TCP's job is not to packetize data. That's the IP in Ethernet that does that. So, but it's hard to think about in terms of, globs of data. So I'm using packets as an example. So for those of you listening on YouTube and whatnot, don't say, oh, but you said it's not a packet. Well, it isn't, but it's easier to understand that, okay? So in the old traditional TCP, so let's think about that 25 packets that left the train at the same time. If train number 5 goes missing and I receive 6 through 25, I throw all that out because I'm still, fixated on train number 5, train number 5, train number 5, train number 5, train number 5. And stupidly, I throw away packet number 6 through 25. Even though they arrived just fine, I throw it out. So then TCP was rewritten to say, okay, that's pretty stupid. Why should we throw out all the data that we receive? So selective acknowledgement came out. So the idea of a selective acknowledgement is pretty simple. I can have little holes in the data, and the acknowledgement will say, look, I received packets 1 through 4, but I'm missing 5. But I'm okay from 6 to 25. I'm not going to throw that out. So when you get a chance, retransmit just packet number 5. Okay, so selective acknowledgement is that. I'm good up to this point. There's a hole that I'm missing, and I'm good from this train to this train. So just transmit train number 5, and you don't have to retransmit 5 through 25. Does that make sense? So here, I know selective acknowledgement is in use because even though there's all these triple duplicates, I'm only seeing one retransmission at a time, fast retransmission at a time. Does that make sense? Because otherwise, in the old TCP, I would have seen everything that train number 5, I would have seen retransmission of 6, 7, 8, 9, 10, 11, 12, 13, all the way up to 25. Okay? Every one of those had to be retransmitted. Make sense? All right. So clearly we have packet loss. We have retransmission timeout packet loss. Highly concerning to me. Okay? And we have fast retransmissions. All right. The other thing that I'll throw out there, and I'll leave this as an exercise for the reader, even though I hated professors in school who said that. It can be easily shown. Well, no, not really, but. So here's a mental exercise for you. We talked about, these army of retransmissions or the duplicate acknowledgements coming. In this case, it's up to 25, 26, 27, 28. Let's go for a record, 29. 29 packets saying, I missed it, I missed it, I missed it, I missed it, I missed, I missed, I missed. So we said after the third one, it gets retransmitted very, very quickly. Right? What happens if that retransmitted packet goes missing? You told me 3 times you didn't receive a particular set of data, so I retransmit it. I fast retransmit it. What if that guy goes missing? I think I heard. Okay, so I heard that. Okay, well, I retransmitted. I did a fast retransmission, and if that retransmission goes missing too, the timeout kicks in, and I'll retransmit. Okay, that's what we see here. You'll see in just a second. The other question is, why doesn't the sender do this? So here's 1, 2, 3, fast retransmit. 3 more feedback, another fast retransmit. 3 more feedback, another fast retransmit. Why doesn't it do that? Because if the rule is, if you told me 3 times you didn't receive a packet, I'm going to fast retransmit. I just told you that these are all packet trains that left that caused these 25 duplicates to come in. So the request hasn't reached the other. So that actually explains why we see, and we're going to measure that in just a second. Okay, the thing was the feedback or the retransmission hasn't reached the other side. So put that aside for the time being. If the rule says every triple duplicate I'm supposed to retransmit, how come I don't see a retransmission somewhere down the road here? Retransmission after this one, after this triple duplicate, after this triple duplicate, after this triple duplicate. What happens? So that was actually a question. I had to go look that up. Okay? And it's very annoying because when you get to the corner case of these cases, it's hard to make sense of it. And there's a quiescent time where once I see that triple dupes come in, the best I could come up with was that there's a quiescent time that says, I don't trust you anymore. I'm not going to automatically retransmit every 3 triple dupes. Okay? And there are consequences to that. Okay? So if you know the exact part of the RFC that addresses that, email me, and I'll add you to my next class. Okay? But that's the best way that we figured by reverse engineering this. Now, I said this was kind of a gnarly trace file because we're about to go into all the corner cases of what happens. And we're also going to show an example how recovery mechanism seems to take a different code path of the IP stack at the other end. So by looking at this trace file, we were able to talk to the vendor and say, hey, when this condition occurs, your recovery mechanism seems to use a different algorithm than when you're sending. And the vendor was like, well, how did you know that? Because the signature changes. Okay? So this is how deep we're going to get. We're going to get going here because I didn't realize we just spent 20 minutes setting up the problem. All right, so it's like a cooking show. We have a cake baking in the oven, and we're going to go to the first example where I ask for a request for NFS reply and request. Okay? So this is the beginning of a request saying, hey, here's my 10 dot guy saying, and then the 192.168 saying, okay, here's my write, and 192.168 saying, here you go, here you go, here you go, here you go. Okay? Make sense? You see that? So this is the beginning of the packet train. The guy says, yep, bring it on, and I start writing the packets. Okay? So let's go through this example. And let me just show this a little bit more. Okay, good. All right, so this is the beginning of time that I'm interested in. And we see here, okay, I'm going to go to a different view. So it's busier, but it'll help us. So I'm going to add next expected sequence number, seek ACK, and next expected sequence number. Okay, so let's go to do that. And that's my normal default. A little busier, but it'll help us troubleshoot because I can keep track of sequence numbers, the next expected sequence number, and who I'm acknowledging for. Okay, so it helps in troubleshooting if I have all this data right at the tip of my finger. So let me just zoom into the packet size here. A little more information to deal with, but again, this is why we build that cache memory, right? So we can quickly look at a busy screen like this and make sense of it. So if I come down here, and this is that packet train, and I get to 749. Oops, sorry. 12749. This is the begin. I see dupeback here under, and this is my first dupeback. Okay, so at some point, a packet went missing and says, "Hey, wait a minute, hold on a second here." Okay, this is my first duplicate saying, I'm missing a chunk of data. But the sequence number that he's complaining about, okay, if I go back up in time, so this is acknowledgement 12719, okay? So the client on the other side said, hey, I'm good up to packet number 12719. So let's go back up to this moment in time, packet number 12719. Okay? And a couple of packets after this went missing, right? Because everybody understand what I'm talking about, right? So I saw the duplicate act happen. So if I follow the sequence number train here, I want you to follow the sequence number, next expected sequence number, okay? And there should be no gaps in time. So I'm going to concentrate on the last 3 digits here. 685 to 133. That's a chunk of data, beginning and end of the data that I just transmitted to you. That's what the sequence next expected is, okay? So 685, 133, 133 to 581, 581 to 029, 029 to 477, 477, 925, 7925 to 9373, 9373 to 821, 821 to 269, 269 to 717, 717 to 165, 165 to 613, 613 to 61. You see what I'm doing, right? Beginning and end, beginning and end. There are no gaps in time here. So what the hell is that retransmission complaining about? There's no gap here. So why did the triple dupe happen? Again, situational awareness has to kick in, and you have to know that this went missing somewhere past my capture point. I sent it to you. I know I sent it to you, but the other side did not receive it. Okay, everybody see that? So this was a particular class of switch where there was a problem. And the problem was packet was getting lost inside the switch, but no counters went off. That's why it made troubleshooting more difficult. And we did it by typing all the various commands at the platform level, hardware level, looking at every ASIC, every counter there is, not just the interface counters, but the ASIC counters, the hardware counters, the platform counters. Okay? Counters didn't go off. And I proved it by putting a capture, the NetShark, on the ingress and the egress of this switch. And I saw it here, not shown here. The only thing in the middle is the switch. Okay? So it's okay that the switch, no switch in the world is line rate. At some point it's going to drop. My only beef was the counter should go off. Okay, so there was a bug in the counter. So that compounded to why this was so difficult to troubleshoot. Okay, so now we know that even though there's a retransmission, okay, it can happen even though you've accounted that there's no packet loss. There's no packet loss from my point of view, but beyond me, there is a problem. So don't forget that. Don't get wrapped around of why is there a retransmission when I clearly sent it to you. Okay, make sense? Yes? Okay. Jesper, did you have a question or comment? No? Okay. All right, so the next one here is that let's go to 12763. And this is my retransmission. Okay? So look at the sequence number, 821 to 269. Okay? So this is a retransmission, a fast retransmission at that. What caused this retransmission? We move up. Those are my triple dupes coming in. Okay. Dupe back number 3 here. So dupe back number 1 is here. And what is it acknowledging for? I'm good up to 821. I'm good up to 821. So clearly, after 821, something went missing. That's what the acknowledgement is saying, right? Hey, I'm good up to 821. But after that, I missed a chunk of data. And you'll notice here, the sequence number 821 to 2269 got retransmitted. That's how you tell. Okay? So how long did this to this happen? Let's measure that. So here's my triple duplicate happening. There's 1, 2, and 3. Okay? So when the first packet loss was detected, which is the first duplicate ACK, I can hit Control T for time reference. So now I've set my control, and you're going to see, why didn't it set that? Yeah, it did. Okay. So from here to, I set the time reference here, and my first retransmission occurred here, all of 21 microseconds. The time elapsed from here to here is 21 microseconds. So clearly, this is a big honking network, and it's a 10 gig throughput network. Okay? So even though it looks like there's a bunch of dupe ACKs, that's how fast this happened. This fast retransmission penalty was 21 microseconds. Everybody see that? Okay? And that's why I use Control T, because if I do this, this is since the beginning of time, and it's hard. Oh, I'm sorry. You know what? I screwed that up, didn't I? So this is a column, and it took 142 microseconds. Everybody see that? So that was in the delta column. Nobody called me out on that. Shame on you guys. Okay. So I set the time reference. So this is the beginning of time now, and 100 microseconds later, the retransmission occurred. Okay. So far, so good, right? And we understand why all the triple duplicate ACKs didn't generate. Okay. So let me turn off this time reference, and let's go to the next point of interest. And that's 12775. Okay. Here, what's happening here? I have a sequence number, some amount of data, and 192.168 acknowledges what? 775. So this is which packet am I acknowledging for? Okay. So you can also look at that from a acknowledgement number itself or the packet number. I use both because it just helps me. Use whatever works for you. This is the acknowledgement number for 30013. The next expected sequence number is 30013. How long did it take from this to this? The delta time is in 197 microseconds. But wait a minute. The rule of TCP says you have to acknowledge 2 full MSS or 2 packets, depending on the OS. Why did this guy acknowledge this packet? Okay, this packet was sent. This one acknowledged it in less than 200 microseconds, less than a millisecond. Why? So that's the question. Okay, it's not number one. It's not a full-size packet. Never mind, just not a full size. There's only one packet because Windows will acknowledge any 2 packet. Linux systems will acknowledge 2 full MSS. But it's a single packet here. 12775, this packet is a single packet, and this guy immediately acknowledged what's going on there. Piggyback ACK. This guy had something to send. Okay? So if I'm going to send you some data, I might as well acknowledge you, right? I'm not going to follow a rule that strictly and said, I'm sorry, I'm not going to acknowledge you because I'm supposed to wait for 2 full MSS or 2 packets. No. Piggyback ACKs happen. Okay, so don't get wrapped around the axle on that one. So since I have data to send to you, I sent you the thing. And then here, the 10 dot guy answered and says, okay, you sent me up to this guy, and I acknowledge you here. Okay? My sequence number goes from 3201 to 4649, and I'm going to acknowledge 4649. Okay, I'm a good up to 4649. Or you can cheat and say this is acknowledging packet number 12776. But it took 100 milliseconds. Why is that? Let me recap. This guy sent the packet. This guy immediately acknowledged. Then the other side acknowledged back, but it took 100 milliseconds. Why? So it doesn't have to do with proximity of closer to one or the other. Why did it take 100 milliseconds? You have to speak up for me. So was it a round trip time? We've established a round trip time already, didn't we? What is my round trip time? Anybody remember what my round trip time is? You're like, Hansang, you didn't measure the round trip time yet. I absolutely did. Microseconds, right? 100 microseconds? Because my round trip time was measured because I saw the 3 triple duplicate acknowledgements go back. and the retransmission happened in less than 100 microseconds or 140, 110 microseconds, whatever it was. That's my round trip time, okay? Because you have to think about this. Again, situational awareness. 3 triple duplicates went to the other side, and a retransmission occurred. That's a round trip event. 3 dupbacks, retransmission. I measured it. It's 100 microseconds. I'm in a LAN environment. So why the hell did it take 100 milliseconds? So penalty because the application is slow? Application delay? It's more basic than that. What's my rule about acknowledging? How many packets do I acknowledge? Every 2 or 2 full MSS? In this case, I only had 1 packet sent to me. So I have to wait for delayed acknowledgement to go out. Because I also don't have any data to send. Remember the rules, right? They trump each other, okay? So, trump each other, that's funny. That word has a whole different meaning. And by the way, let me just take the time to apologize. The 2 worst candidates in history going at it. So I'm not going to go off on a rant here, but it is a little bit embarrassing. So be that it may, the rule says you must acknowledge 2 packets if you're Windows OS. If you're a Linux system, 2 full MSS. It's no good if you send me 2 small packets in the world of Linux. I still need 2 full MSS. And if I don't hear from you, I'm going to wait for a delayed acknowledgement timer to go off, and then I will acknowledge you. Okay, that's the rule. So here I sent a small packet, 164 bytes of data. I immediately acknowledge you because I had something to send. This is a piggyback act. I have something to send to you, so I will just acknowledge you. But this packet that's highlighted here, the 10 dot guy doesn't have anything to send back. But he only saw 1 packet only, so he sits there and waits until the delayed act timer goes off, and then I acknowledge you. Okay? Because I had nothing to send to you. So this is the opposite of an application delay. If the application had something to send back, he would have piggybacked the acknowledgement. Make sense? Okay? And then 192.168 sends 2, and then he acknowledges that, doesn't he? Okay? 1, 2, 3, acknowledgement. What's happening here? I send 1 packet, 2 packet, 3 packet. What's going on? I'm sorry? Slow start. Because there was a packet loss and a timeout condition, my congestion window gets trimmed down, and my slow start threshold gets trimmed down, and I start to ramp up again. Okay? Everybody see that? What's happening here? 1 packet, 2 packet, acknowledgement, etc. Okay? So this is the kind of the beginning of the slow start, right? Yes? So, let's look at, I'm looking at my notes here so I can cut to the chase. 12780. All right, so here. This guy is, so this packet here, 12780, is acknowledging which packet? The answer is right there. 12779, the previous packet. Okay? So let's rewind the clock and take a look at this. So when I go back here, I've acknowledged packet 12776. I'm all caught up. At this point, in that direction anyway, I'm all caught up. This guy sends 2 packets. Okay? Never mind 2 packets, it's 2 full MSS packets. And the acknowledgement comes back, but it took 100 milliseconds or 90 milliseconds. What the hell is that about? This is breaking the rule of TCP. I have 2 full MSS packets that I just saw. This one and this one. And yet, my delayed acknowledgement kicked in. Because he's saying, look, I'm acknowledging packet number 12779, or up to acknowledgement number 7545, which is here, 7545. So I acknowledged it, but it took 90 milliseconds for me to do that. Why? So that's my first question. Why did you take 90 milliseconds for you to acknowledge me, even though I sent you 2 full MSS? That's a rule that you should never break. I gave you 2 full size. Your job as a stack is to acknowledge me right away. And I know my round trip is in microseconds. So why did you take 90 milliseconds? Why? What else can we do here? So was there a buffer along the way? Maybe, okay? Maybe it was buffered, but I'll tell you this, 90 milliseconds, there is no networking equipment in the world that can hold on to a packet for 90 milliseconds. None. Zero. Nada. So why did it take 90 milliseconds? Okay. This is breaking the RFC. 90 milliseconds is too long. So let's see what we can dig around here and see what the hell might be happening. Okay. What can we use from a TCP and IP stack perspective to see what might be going on at the application and TCP stack layer at the other side? What does the 192.168 and the 10 dot guy use to determine how busy the other guy is or not? Window size, right? Because when the window size goes down, what's happening? So again, this is the reason why this is so gnarly and can be interesting, even though I'm running out of time, damn it, is window size can tell me what's happening at the other side, okay? So I'm going to cut to the chase. As I was looking at this trace with my team, we all stopped and said, why the hell did that take 90 milliseconds? Makes no sense. So let's see what might have happened to the other side. Okay. So here, the 10 dot window size is 48,621, and 2 packets showed up, and his window size went to 47173. Notice here, 1717, right? So here's 48,621 and 47,173. Window size going down is fine. That's just the receive buffer working. There's too many people coming in. I queue you up inside my receive buffer, and my window size goes down accordingly. Okay, it's just like when I came in through immigration. It said here, the wait time from at this point is 10 minutes. That's my receive buffer being used. It's okay. And your window size is supposed to go down. Okay, so let's go back a couple of packets before and see what the window size action looks like. 65535, that's a full window size. The fact that the window scaling factor is unknown because I don't have a Cincinnati, immaterial. Okay. So keep an eye on this 65535. Window size, full 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 window size. Even though if I go up a few more frames, I'm sending you a bunch of packets, the window size did not go down, meaning he's ingesting that as fast as you're sending it. The receive window size is never kicking in. The receiver is not queuing up any packets in the receive buffer. Okay, he's just picking them off as fast as you're sending, and so the window size never goes down. But from here, where I have a 90 millisecond delay, what's my window size here? 48,621. Okay, and what's my window size here? 47,173. So let's do that. 47,173. To 48,621. The difference there is 1448. Why is that 1448 number significant? Because that's the full MSS. Okay? So what just happened? Up here, the 10 dot guy is saying, bring it on. My window size, I don't even have to queue you up because I can acknowledge you as fast as you're sending me. My window size never goes down. Then all of a sudden, we have this 100 milliseconds, no less. And I sent you 2 packets, and you slowed down your window size. So even though 90 milliseconds went by, what is this telling me? 90 milliseconds went by, but fill in the story. What happened on the 10 dot guy? I sent you 2 packets, 1448, 1448. It's not the same packet because my stair stepping of sequence number 649, 97, 97 to 45. These are 2 contiguous packets that I sent to you. And what did you tell me? What did you tell me right here? You picked up the first packet, but you queued up the second packet. That's why the window size went down by 1448. So even though you had 90 milliseconds to deal with these two packets, you managed to pick off only one packet of the two that I sent to you. I sent you this, I sent you this, but your window size decreased by 1448. What does that tell me about that 10 dot guy? He was so busy that for 90 milliseconds, he only picked up the first packet that I sent to you. Something seriously is going on there. Everybody see that? Okay. Yep. Okay. So normally, you would have just said, hold on, it doesn't make sense. I sent you 2 full MSS. You're supposed to acknowledge me right away, but you didn't. And on top of that, this is a naked acknowledgement. There's no data that he was piggybacking. Okay? Even if it was a piggyback act, TCP says 2 full MSS, you're supposed to acknowledge, but he didn't. Something went wrong with that 10 dot guy. Okay? We know that for a fact because of window size. So this, what happened here is he picked up this, gave it to the application. This one showed up, and he queued that. He queued it, and that's why my window size went down. Okay? So this is why I was able to go back to the vendor of the 10 guys saying, something is wrong with your box. Everybody understand that, right? Now, it's easy when I'm up here showing it to you point blank like this. But it's not so easy, okay? But this goes back to my annoying, loving 4-year-old. Why? When you see 2 full MSS and there's a delay, investigate. It's not normal, okay? If you've ignored it, you know, this troubleshooting would have went on much longer than that. Okay? All right, so let's go back to, in my note it says go back to 12693. Why? Because this is the beginning of a normal transfer looks like, okay? So you can see a bunch of things happening here. And the acknowledgement happens saying, hey, I'm acknowledging up to packet 12695. Let's go back to 12695 here. Okay? So this is the first acknowledgement of this packet, 12695. And so we see here full size, 2 packets, I've acknowledged it. Okay? Let me reiterate what just happened. This packet went, and down here it says, I've acknowledged you. Okay? Why is that significant? Because let's do the window size analysis again. Previous to me sending you this data, my window size was 33580. When you acknowledge me down here, 33580. So you were able to keep up with 2 packets that I sent to you. This is the normal condition. I sent you 2, window size didn't go down because what's 2 packets to a modern day server infrastructure? So clearly this is a normal use case, but in my other example, there was a 90 milliseconds where a packet got stuck in the queue. Okay? So I've proven beyond a shadow of a doubt this box can keep up. So that 90 millisecond was an abnormal condition. Okay? Everybody understand that, the significance of that, right? Okay, so now I'm going to jump ahead to 12795. All right. So here we see a bunch of senders and acknowledgments happening. And let's do the window analysis again here. 38485, and this guy is 42103. So what's the difference? 42105 window size here. Okay. Right? 42105 is my window size. And the one previous to that, or this one, I guess, is 38485. $36.20, which happens to be what? 1448 enter 2 times 20. Oh, sorry. Did that wrong. Was it this one? Yeah, sorry. Let's look at this one and this one. Okay. 38485 42105. Okay, window size. So 42105, enter. The next time the 10 dot guy sends me an acknowledgement, his window size is at 38485. Subtract 3620. Does that divide evenly into 1448? 2.5. It's not. So why is that significant? Why is that significant what I just did? So the acknowledgement got lost? Is that what the acknowledgement was lost? You're getting what? Okay. Okay. Then, well, here's the thing, though, right? What happened between here and here? I sent you a bunch of data, okay, all full size, but the window size decreased by 2.5 my MSS, which means what happened? Is that normal or abnormal? Yeah, he didn't put the whole packetized worth of data to the application. He's streaming it in, which I don't think that's illegal. So the receive buffer is just a bunch of people in a line, okay? And the application is saying, hey, you first row here, come up. Almost always that's in a packetized format. I send you 1440 bytes of data, 1440 gets acknowledged. The next 1440 gets picked up, okay? In most cases, that almost always works that way. But in this case, for some reason, the 10 dot guy said the first two rows and then half of the third row. That's my 2.5 times MSS. I haven't seen that. So now I'm starting to doubt, what the hell is wrong with this 10 guy? A, you only took, in one case, you took one packetized amount of data and queued up the second one. That's the 1448 reduction of TCP window size. Here, my window size is difference by 2.5? Yes.
What if there are other clients talking to that server and the server reduces the window size not just by the amount of data that it is getting from you,
Okay.
as a total between all different clients connected?
Okay, so the question was, what if the server is talking to other people and it's impacting the window size? The answer is it can never impact the window size because the TCP socket is unique and the TCP window size is reserved for me and you for that conversation only, okay? So the fact that he's talking to other people doesn't impact my window size because here's what happens. When you first open up a TCP socket, you reserve a send buffer and I reserve a receive buffer. Okay? Your send buffer and my receive buffer is unique to that socket. Okay? And this is why you shouldn't open up your window size to be 2 billion because every time you open up that socket, you have to reserve that much in reserve space. Okay? So does that answer your question? But he brought up a good point. How busy is this guy? Is he servicing other customers? And the way you can kind of infer that is by looking at the IP ID. IP ID is not unique to the conversation. IP ID is unique to the box. So if I have 10 people that I'm talking to, 10 different sockets, I use IP ID 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so the IP ID is common to the box, not to the socket. So here my IP ID is 30,000 or so, and here my IP ID is 57,000. So in between this and this, there were 20 some odd thousand other packets that this guy had to talk to other people about. So it's a pretty busy guy. It may be more than that because the IP ID recycles after 64K, and so it could have looped around twice even. Okay, so I know this 10 dot guy is busy. Because how much time elapsed from here to here? 100 milliseconds. That's a pretty long time. And he also had 25,000 or so other packets that he sent out. Does that make sense? All right. So what else is going on here? Let's take a look at... Oh, my God. I'm over time, aren't I? So, okay, let me just show you this one other thing, and then I'll let you out. I'm sorry, and then... This always happens. That's why I asked Janice for 2 packet, and then some idiot came in late. And all right, if you ever bring that up, I'll deny it. So the other one here is if we go to packet number 12774. Okay, let's do that. 12774. And if I look at the window size, okay, so here's a bunch of packet trains that I'm acknowledging. My window size, keep an eye on down here, 65535, 65535, 65535, 65535, 65535. Boom, boom, boom. Oh, right there. See the window size decreased by 49. Okay, from here to here, the window size decreased by 49,000. I'm sorry, it went from 65535 to 49,000. Okay, why did that happen? All of a sudden he couldn't keep up?
I think you got 25 more minutes.
Oh, I do?
As far as I can tell, you're on till 12.
Oh, 12. So I have 8 more minutes.
12, 15.
Oh, 12. Okay. Well, that's all you have to say. All right, so we'll calm down a little bit. So let's go and take a look at this. Okay, let's take a look at this. So this is is this a retransmission? Okay, let's scroll over to the right. It's a fast retransmission. Okay, so it's a fast retransmission, so we know there are not too big penalties to be paid for that. And this fast retransmission is for sequence number 821. I scroll up, and I'm going to find 821 up here. Okay? Somewhere up here, I'm going to find the same sequence number that ends in 821. Okay? That's fine. So this chunk of data went missing. Okay? And then I see here, I'm acking all these dupacks. Okay? As he's dupacking, guess what I'm going to see in these dupacks? Because what's happening? 192.168 sent a bunch of data. 25 trains left the station. One of those went missing. The 10 dot guy's job is to say, I'm good up to this point, I'm good up to this point, I'm good up to this train, I'm going good up to this train. Oh, I have a packet that went missing, but I continue to receive trains. Right? In the old days, what would have happened? I would have thrown everything out beyond that missing point. But here we talked about what that's in effect? SAC. Okay? So 192.168 is the this is the fast retransmission that occurred. It's right here. So let's roll up a couple of packets above that. Shall we? Okay. So 192.168 retransmitted down here. He was retransmitting originally here. Okay? And we see here a bunch of packets coming, and the 10 dot guy is acknowledging as best he can. He keeps doing that. And then right here, we see the first duplicate act number 1, number 2. This is the first time the other guy told me, hey, I just experienced packet loss. And if I look at his TCP sequence down here and look at the option, he's telling me, yep, there's a slice of data that I'm good for, but I have a gap because you're sending me other trains are coming into the station, but there's a gap, okay? So keep an eye on this SAC number here, 69 to 65. 69 to 613, it went up. 69 to 0861. 69 to 9509. What's happening? Yeah, my right edge is going up, meaning I'm good, I'm good, I'm good, I'm good. This is telling me this is good here. I'm good here. This is my next chunk of trains that showed up. So what this is saying in layman's term is this. 1 and 2, ACK. 3 and 4, ACK. 5 goes missing. 6. I'll acknowledge 6, but I'm telling you 5 is missing. 7, 8 shows up. I'm good from 6, 7, and 8, but 5 is missing. Okay. 9 and 10 show up. I'm good from, I'm keeping lost. 6, 7, 8, 9, 10, but 5 is missing. 2 more packets show up. I'm good from 6, 7, 8, 9, 10, 11, 12, but 5 is missing. So that right side keeps getting bigger and bigger. Okay? So does that make sense? Okay? Yes, question.
What happens if you have more than one packet or more than one string?
Okay, so what happens if more than you have multiple gaps? What you're going to see is additional line of SAC here that has, I'm good from train number 5 to 8, but I'm missing 4. And then you're going to see another SAC line that says, I'm good from, the 5 and 8 is good. And then there's another chunk of data. So you're going to see another SAC where you're going to have spots of SACs happen. It doesn't go up forever because obviously the TCP header is limited to 40 bytes. Yes.
So even though you have 2 consecutive packets being lost, there's going to be 2 lines.
So no. So if it's so the question was, I have 2 packets that went missing. Would I have 2 SAC lines, 2 consecutive lines? What happens if 2 consecutive lines go missing? I'm sorry, 2 consecutive packets go missing. What would the SAC look like? So a double set of left and right, meaning 2 lines of SAC? Okay. Anybody want to agree, disagree? How about this? Let me ask you this way. If you sent 2 small packets of data, so let's say you sent 250 and 250. Okay, so because the application was unwilling to send it in one shot, the application gave you 250 bytes of data and 250 bytes of data. And it was sent in 2 different packets. And they both go missing. What does the retransmission look like? Okay, so there's one. Anybody want to disagree or agree? So the retransmission data packet, how much data would he carry? So that was my question. Is it done in 2 steps or is it done in 1 step? Okay, so I'm going to call him out on this because the answer was, well, the application can decide to retransmit this amount of data, the segment that went missing. And the answer is absolutely wrong. Application is not involved in the retransmission. Why? Who's in charge of retransmission? TCP. Okay, so let me take a step back and reiterate what the TCP's job is. TCP has a send buffer. Okay, and you need to visualize this because we need to be very accurate when we're describing problems. Okay, because even though your philosophy or the spirit of what you said is correct, it's technically inaccurate. Application can't guarantee delivery. He uses TCP for that. So when TCP receives a set of data, he opens up a warehouse full of shelves. And his job is, before he sends that data out, he makes a Xerox copy and puts it into shelves. And the shelves are numbered by how many bytes of data I transferred. Okay, so everybody in this room, sitting in a row, you're my send buffer. As the application gives me data, I start to Xerox copy and fill every one of the seats that are in rows here. Okay? You're my send buffer. And I have from byte number 1 all the way to byte number 1,000. Okay? At this point, the packetized data doesn't matter. I don't care about packets. I'm only keeping track of bytes that I transmitted. So keep that in mind. Even though I said I'm going to use packets as example, I'm not keeping track of packets. No one's keeping track of packets. I'm keeping track of how many bytes I've transmitted. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 people per row. Okay, that's my shelf space. And I have 10 of you. That's 100 bytes that I can hold on to. So when the application gives me data, 100 bytes, I Xerox every one of those 100 bytes, fill every one of the seats in here, and I transmit. And if the receiver says, hey, I missed byte 50 to 75, I go to my warehouse, I find bytes 50 to 75, and I retransmit that byte. So if it's contiguous, TCP can and will clump it up and retransmit it as one packetized data. I say this because be careful when you're looking for sequence numbers. Okay, one of the ways you can find retransmission is to look for this sequence number again. You may not see that sequence number. Why? Because 2 packets went missing, and the sequence number that you're looking for was repacketized as part of 2 packets that got sent into 1. Does that make sense? So your original sequence number doesn't show up because your sequence number was 10 to 25, 26 to 75, and then now it's being retransmitted as one big chunk of 75 bytes of data. Okay? So keep in mind in your head, you're keeping track of bytes sent. So in my send buffer, I'm keeping track, and when a packet, the data that I sent goes missing, I go to the Xerox, make another Xerox copy, and I transmit. When you tell me you're good up to 75, sequence acknowledgement number 75, I wipe out data from 1 to 75, I clear that space, and what have I done? I've made space for 75 more bytes of data for the application to give me so I can guarantee delivery. Okay? This is why the send buffer is so important. Unfortunately, it's never exposed in the packet, but it's almost always the receive window size the same. So I do this so that I can guarantee delivery. Okay? But if there's non-contiguous packets that go missing, I will have 2 distinct lines of SAC. I'm good for the first row. The entire second row went missing. That's my left and the right edge. So I'm telling you, first row worth of data, however many packets that is, okay? In our case, it's going to be 1 for 1. So the first 10 packets are okay. The next 10 packets went missing. So I have a line of SAC that says, I'm good for the first. I'm missing an entire second row. I'm good up to third row. Okay? So my SAC will say, from the starting point of 21 through 30, I'm missing that. That's my entire hole of data. Another row comes in. Okay, I still have a hole. The second row is a hole. The fourth row is okay. The fifth row goes missing, so now I have 2 SACs. The entire second row is missing. The entire fifth row is missing. So I'm going to have 2 separate lines of SAC because they're non-contiguous. Okay, make sense? Okay, so let's see that in action, okay? Because we're concerned about window size too, right? Because we already know this window size is kind of squirrely. Sometimes he consumed 2.5 MSS worth of data. Sometimes he had 1448 bytes worth of data hanging out in the receive buffer for 90 milliseconds. Something squirrely is going on, so I'm going to concentrate on the TCP window size. Okay, does that make sense? Yes, is there a question or stretching? Stretching, okay. Nothing wrong with stretching. So here's 65.5. And by the way, I said, window scaling is unknown because I don't have a TCP handshake. It's immaterial. Why? Because it's a scaling factor. I'm still keeping the number of bytes being transmitted, okay? Okay, so I get 2 packets here, and this is my duplicate ACK. My window size is still good, 65535, okay? All right, I'm not going to go into that. And then here is 65535. And where's my, so this is my dupack number 1. And if I go down to this, if I go to my left and right edge, it's starting to go up. The right edge is starting to go up. So let me go to a view that shows that so we can see it more clearly. So now I've added the left and the right SAC column. Let me increase my font size just a little bit. Okay. So look what I'm doing here. Okay, where's my retransmission? This one, right? So let me mark that, Control M, so we can clearly isn't that? I thought I marked it. Okay, well, I don't know why it's not marking. When I hit Control M, it should turn that whole entire line black, but it's not. It's odd. So let me manually add it. Okay. So for some reason, my Control M is not working, but I think that's my problem. So you notice here, that's my fast retransmission, right? The black bar there, I marked it so we can, even though when I'm scrolling up and down, I can quickly find that guy. All right, so here's my left end SAC kicking in. Notice what's happening here. This is my beginning of the goodness. I'm good from 269 to 61, 69 to 509, 69 to 957, okay? So there are a couple tricks that you can use. What's my MSS here? MSS in use is what? 1448, isn't it? Okay? That's my full payload size. My train can carry 1,448 passengers in a particular car. Okay? Make sense? That's my full MSS. So, the full MSS is 1448, so it ends with an 8, right? So as a quick test, if you add 8 to this 1, what do you get? 8 plus 1 is 9. 8 plus 9 is 17, ends with a 7. 7 plus 8, 15 is a 5. 5 plus 8 is 13, so it ends with a 3. 8 plus 3 is 20, or not 21, 11 ends with a 1, and it ends with a 1. So what's happening here? He's acknowledging every other packet that's coming in, saying, I got it, 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 I got it. My SAC window is getting bigger and bigger, saying, I'm good all the way. This is all the data that I would have had to thrown out in the old way of doing this. So I'm saying, I'm good, I'm good, I'm good. And all of a sudden, down here, my retransmission starts at what? 821 to where? 69. Where have we seen this number before? The left edge. So this is the hole. This is the hole that I've been keeping track of. I'm good from here to here, 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 here to here. But previous to 69, okay, previous to that, I have a hole. That's what the SAC is telling you. This is the goodness, and then I catch up here. So I send you from 821 to 269, which then completes 269 to here. Okay, let me repeat that. This is the missing chunk that got fast retransmitted. Okay, so in terms of number of people sent, number of bytes sent, 821 to 269, and then 269 and continues all the way up to here. I've caught up that missing hole, and that's what that missing hole represents. Okay, this is why SAC is so incredibly powerful. Okay? Did everybody understand that, or should I go? Yes, question. You have to speak up, though, because I have... So say that to me one more time, but a little bit louder, please, so I can... So what must get reduced? Oh, window size. Oh, okay. So that's a different question. So the question was, should the window size decrease as the SAC is increasing? Okay, let's think about that. And we can prove it, by the way, right? Because we can. So the question was, as my SAC is getting bigger and bigger, will my window size get smaller and smaller and smaller? That's the question. Okay? Let's think about that. Should that happen? A, we can prove it. Let's just look at the window size, right? As my SAC is getting bigger and bigger, 65535, 65535, 65535, 65535, 65535, 65535, 65535, 65535, 65535. It's not decreasing. Why isn't it decreasing? Okay, and then in the back there?
Yeah. So when you have the window size, that is how much the data to the other end can send without waiting for acknowledgement. The SAC does not change how much data has been acknowledged from the get-go consecutive until this point. The SAC is merely, you do not have to retransmit this.
Okay.
The client can still only send from what has been acknowledged up to that window size.
So
It does not have to retransmit. The SAC is only a tracking
Okay. So we're going to do this. I'm going to leave this as an exercise for you guys. So there's two things that were brought up. Okay. As SAC is increasing, why is my window size not going down? And the other answer was SAC has nothing to do with the receive window size, because window size is a receive function. A SAC is keep telling the other side that there's a hole in my data. Okay. But what is it? So the question is? So SAC is keeping track of a hole. Okay. I would buy that. But so let me ask you guys a question. And let me ask you a question because you asked that question. Why did you tie the SAC with the window size? So you asked me, right? SAC is getting bigger. Why isn't the window size decreasing? Okay. So let me just cut to the chase and say, wait a minute. Why isn't there a window size impact when the TCP stack cannot give this application out of order? TCP cannot send data to the application once you've received it out of order. Why? That's your job, to reorder that data. Right? In other words, I have a receive buffer for a reason. Because if something comes out of order, my job is to reorder them and give it to the application in a nice, neat bundle. So the question was, why isn't that TCP window size not decreasing when clearly I have a gap in my receive buffer? So both answers, question and answer, is right. SAC is keeping track of what I'm missing, and the receive window size is the receiver, how much data he can consume. The receive window size is me telling the sender, I have this much buffer in my Windows receive buffer. Okay, so the fact that there's something else or buffering going on is immaterial because TCP accounts for that. But here's a big lesson that you guys should, to put into your memory. When you have buffers, you're cheating TCP. How many of you heard, and I'm going to come back to this question about the SAC because it's a very interesting topic. How many of you heard the bandwidth delay product? Right? You multiply the minimum bandwidth times the delay, round trip delay, and that gives you the window amount of time, to fill the pipe, right? That's we've all heard. But then what's the typical advice that you see? Don't make it one time the bandwidth delay product, make it 2 times the bandwidth delay product. So bandwidth delay product is this. Bandwidth delay product says, as I'm sending you data, the packet train's leaving, I have to make sure I keep sending until the acknowledgement comes back to me. Okay, I don't want to stop. I don't want to stop the packet train in one-way direction, meaning it takes me 100 milliseconds to go from point A to point B. I want to keep transmitting for at least for 100 milliseconds because it's 50 milliseconds going there, 50 milliseconds to come back. Okay, that's 100 millisecond round trip time. Okay, I don't want to stop transmitting at 50 milliseconds into it because I have to stop transmitting for that acknowledgement to come back for another 50 milliseconds. So the bandwidth delay product says, make sure you have enough data and buffer size, the window size, send and receive buffer, by the way, to transmit for 100 milliseconds duration. Okay? That's a bandwidth delay product. But then the textbook says, make it 2 times bandwidth delay product. But why? Mathematically, I just told you that as long as I transfer data for 100 milliseconds, that's my round trip time, I should be okay. And then I turn right around and say, yeah, but you know what? Make it 2 times bandwidth delay product. Why? Buffering that happens along the way. We've all increased our output queue size. We have individual hardware buffers. There's software buffers. There's quality of service buffers. It's a pain in the ass. When you do that, you artificially elongate the amount of data that can be transmitted. Meaning the receive buffer might say I'm good for 64K, but all along the way, everybody's buffering a little bit of data. Okay? And this is why, to make sure you get line rate, you just blast it with 2 times the bandwidth delay product to account for little chunks of buffering going on at individual data. Okay? So think of it as, that bendy straw that you see, right? And then when you zip it out and pull it out, the straw gets longer. Okay, that's what the buffering is doing across. The hell is this? I'm a little bit worried because I don't know where that came from, but yeah, I've never seen that before, so huh. So what I'm saying is, the reason why you make it twice the bandwidth delay product is you can fill those buffers along the way, okay? Because the round trip time is not 100 milliseconds, it's 100 milliseconds plus all the time you can be spent inside those buffers along the way. Okay, that's why you make it 2 times bandwidth delay product. So getting back to my original question, I cannot send my receive buffer because I have a hole. I can send up to that hole. Okay, so if my first row is okay, I can give that to the application. But I now have a hole. I now have a hole because in my second row of data, the first person is missing. Everybody else is good. Right? Can I send all that data that's coming in when I have a hole in my data? So in your mind, I want you to picture this. For those of you on YouTube watching this, everybody here in the room, the first row is a contiguous set of bytes. Okay? I can send the first row to the application. They're all in order. I have a hole. The first person sitting on to my right, to your left, that's a hole. That went missing. And my SAC starts to say, yeah, I know I have a hole, but I'm all good up to the first 2 rows of data, the second and third row of data, minus the first person. Everybody get that? Okay. So do me a favor, please. The second row right there, where I'm pointing to, stand up for me. You're my hole. Okay? And the gentleman in the red t-shirt, the one row over, yep, the red shirt, stand up. That's my SAC right there. I'm missing him, but I'm good from everybody else after that. Can I send that data up to the application? I know my SAC is increasing, but I have a hole. Can I send that whole second row and third row to the application, yes or no? No, you cannot. How do I tell the other person that I'm buffering data? Receive window size. But my receive window size is not going down. Why? Okay. So that's technically all correct, but it still doesn't answer the fundamental question that I posed. Everybody from that point of missing person, first packet, and I'm sacking you, and that's great, but can I release that data to the application, yes or no? No. Which means, what am I doing with my receive buffer? I'm filling it up. But why isn't my receive window going down? Okay. So never mind that. Answer this fundamental question. Everybody sitting in this table here is my receive buffer. That's it. That's all I have. I can't magically create more buffer space. And you can send me all the data for the one person here missing, and everybody else is sacked. That's great, because as soon as that person comes in, what can I do? Send the whole entire thing to the application, right? But what am I doing in that time? My window size is what? Filling up. My receive buffer is filling up. I cannot release that data. So why isn't my window size going down here? Okay? This is my SAC. This is, from this point on, I'm saying, yeah, I'm good up to that right edge. I'm good up to that right edge. I'm good up to that right edge. But where is this data sitting right now? Okay. Window size must be bigger. And here, the window scaling factor is unknown. So I'm here to tell you there is window scaling going on, but the maximum size of window size that I can show you without the windows. You can sit down now, gentlemen. Thank you very much. Does everybody understand this? This is why you have to know the protocol and you have to look for the Occam's razor, right? Given two plausible answers, the simpler one is almost always right. Okay? So you are very correct in, and it's on my note here, wondering why the window size is not increasing or decreasing. Okay? When it's decreasing, that's okay because those are actual number of bytes that are decreasing. But when it stays pegged at 65535, that's a boundary number. That's a 2 to the, number, right? So we should all know these numbers. And the reason why it's not going down is because I must have more buffer space, but I can't show it to you because I don't know what the window scaling factor is. Meaning, even though this is as 65K, because the window scaling factor is not known, this could be 128K. This could be 256K. This could be 512K. I don't know because I don't know what the scaling factor is. I know it has to be bigger than that because while this is happening, the window buffer, receive buffer is filling up because I cannot release that data until the missing person shows up. Then I can release the whole bunch. Question?
So if you receive the SYN packet, you would see the increase?
Absolutely. If you see the SYN packet, you would absolutely see the scaling factor. Okay? But without the scaling factor, I don't know if it's 2 times the window size, 3 times the window size, 4 times the window size. And I can only show you the maximum that I know, which is 65535. Question? It should go down anyway. Should it go down anyway?
It's going down on the bigger number, but maximum we can set this maximum surely.
It's decreasing, but in a value that it can't display, so it's displaying its highest.
Okay. So we have two. We have a value that's decreasing, but I can't show it to you because I still have a scaling factor going on. The question in the back of the room.
Yes, the window size is decreasing, and the problem, I think, is you can see the decreasing if you don't know the scaling factor first when it's too late. So we maximum see 0 window size off.
So I'm sorry. Start from the maximum. Maximum which one?
From the if we have window scaling,
Yeah.
we don't have the scaling factor.
That's right. We don't have a scaling factor, so we don't know what the true window size is.
Often we see that there's a window, receive window program first when there comes 0 window size or close to 0 window size.
Okay. Okay, so there's a bunch of things that were thrown out there. The one thing that I picked up on was 0 window size. We all know what that means. That means shut up, I can't talk to you anymore because my window is full. We don't see that here, so we're not exhausting the buffer size, okay? But I am telling you that all these SAC, someone has to hold this. When you see SAC, the receive buffer is holding that because the definition of SAC is there's a gap. And until this guy shows up, I can't release the whole thing. So what happens here? Okay, does that make sense? Okay, so you're both actually correct. SAC and receive window size are 2 different things. SAC is telling you what when missing, window size is telling you how much I'm buffering. But there is a dependency between the two. Yes? Why does the window size go up and down previously when we saw it? Because we're looking at it from 65535, but if it dips below 65535, I still have to account for that. So the decreasing is okay. Okay? So that means I'm going down, getting down close to beyond the, but remember it's a scaling factor, right? So it's a scaling factor means my window size times a multiple. So when the window scaling when this window size goes down, there's actually an amplifying effect because that's not my window size. There's 2 times that, 3 times that, but it's still going down. But if I'm very fast and I can keep up with it, it's not going to go down. Okay. So you know what? We'll have this discussion a little bit later, during the after hours. So because even though we are over time, yeah, I'm sorry. So the last thing I wanted to show you was, the ability to do left and right edge. And the idea here is this. When this problem went away, I noticed that the VMs were rebooting for troubleshooting purposes, and the transfer time was fine. Okay? And then all of a sudden, it went back to bad again. So I went back to time and picked out the Cincinnati. When I didn't have a problem, Windows scaling factor didn't kick in, because these two systems, when it couldn't connect because a spanning tree was blocking the port, even with a fast spanning tree, it was sin. I give up. I'm going to go without the SYNAC, without the RFC 1323 extensions, and transfer was fine. The minute RFC 1323 kicked in, I can do the SAC and the Windows scaling factor, the throughput tanked. Why? Because I'm not taxing my 10 gig network. When I'm not Windows scaling, my 10 gig was able to keep up just fine. When I Windows scaled, too many trains left the station, causing microburst condition and packet loss. So in this case, smaller window size actually allowed me to tread water, and the transfer was faster. Okay? So the whole point of this exercise was Windows scaling is good, but not if infrastructure can't keep up, because you're making your problem worse by adding more data to a device or infrastructure that can't keep up. Okay? Make sense? So that was my I do have packet tracers with a Cincinnati, but that's my point. Sometimes too much data is a problem, and you may not see that without microburst studies. Okay? So sorry I kept you guys longer. I apologize. I'll clean up this